Hi everyone, welcome to the another session on low power VLSI design. In previous sessions, we discussed about the types of dynamic power dissipation and the types of in static power dissipation. So, coming to the static power dissipation, so this is the diagram related to the static power dissipation, and the static power is also known as leakage power dissipation. First of all, the static power means so here the circuit is in on state, but that is not doing any action. That is not in the active state. So the circuit is on, but the signals are not switching. Then also it will releasing some sort of power. That power is called static power in the form of leakage power dissipation. So in deep submicron devices, these leakage currents are becoming a significant contributor to the power dissipation of the circuit. Means if you consider the formula for power dissipation, that is equal to the dynamic power dissipation plus static power dissipation. In olden days, um, the leakage currents are negligible, but whenever coming to the submicron technology, the currents are also nearly equal to the dynamic power dissipation. So that's why if you reducing that leakage power dissipation, you can reducing the overall power dissipation of the circuit. That's why we should focusing on um, how that leakage power is occurring and what are the different ways to reducing that leakage power. So these are the different types of leakage currents occurring in the mass device. Already this is discussed in the previous session. Now moving to this type. So in there, the major thing is here I3. So I3 is so I1, I2, I1 R2 are the junction leakage currents. I3 is the sub threshold leakage, and I4, I5 are occurring due to the reducing the oxide thickness and hard carrier junction, and I6 is due to the drain and gate field, and I4 is short channel devices. I7 is for punch through effect, uh, that is occurring in the short channel devices. Coming to this majorly on subthreshold leakage. So subthreshold leakage, this is the important one. The subthreshold leakage in CMOS circuits is due to the uh, carrier diffusion between the source and drain regions whenever the transistor is in the weak inversion. That is, whenever you are applying voltage at the gate terminal is less than the threshold voltage. That means whenever an input voltage, that is gate voltage, is below the VT threshold voltage, then this subthreshold leakage current will occurs in the device. Means your input voltage is less than the threshold voltage, then it will occurs. So at the situation, the behavior of the mass transistors in this subthreshold region is similar to the BJT, and the subthreshold current exhibits an exponential dependence on gate voltage. So the amount of the subthreshold current is become more significant when the gate to source voltage is smaller than or very close to the threshold voltage of the device. It is very close to the threshold voltage or smaller than threshold voltage of the device. So various mechanisms which have the effect that the subthreshold leakage current or a drain induced barrier lowering, body effect, narrow width effect, effect of channel length, and effect of temperature. These all are different mechanisms which will affect in subthreshold leakage. First for drain induced barrier lowering. So here, if you consider long channel devices, the source and drain regions are separated far apart, and the depletion regions around the drain and source have little effect on potential distribution. So if you, whenever you are considering the long channel devices, the distance between the source and drain regions are long. Those two are separated by uh, some long distance. At that situation, the depletion region around the source and drain terminals have little effect on the potential distribution in the channel region. So the threshold voltage is independent of the channel length and drain bias for such devices. But however, for short channel devices, the source and drain depletion region width in the vertical direction, that is, the distance between the source and drain is very less. That's why these are called short channel devices. So the potential effect, uh, is more in the short channel devices, and this is leading to the um, variation of the subthreshold leakage current with the drain bias. So if you changing the voltage at the drain terminal, this will um, changing the values at the bias. This is called drain induced barrier lowering. Means for the short channel devices, the distance between source and drain will be less. Due to this, the depletion region width in the vertical direction and the source drain potential have strong effect on significant portion of the subthreshold current, that is due to the drain bias only. So whenever you are applying the voltage at the drain terminal, this will affecting the uh, devices those are having short channel, and the width of that depletion region width is more. So that's why this is called drain induced barrier effect. So because of double effect, the barrier height of the short channel devices reduces and increases the subthreshold current due to the lower threshold voltage. So dibble occurs when the depletion region of the drain and source interact with each other. So whenever you are increasing the reverse voltage, the depletion region of the drain and source are nearly connecting the each other. So interact with each other. So the channel surface to the lower source potential barrier. So dibble is nothing but whenever you are applying that input voltage at the drain terminal, the depletion regions at the drain and source, the both are uh, connecting each other near the channel surface. Due to this, leakage currents will occur. Um, those leakage currents are subthreshold leakage, and this is induced because of this drain voltage only. That's why this is called drain induced barrier lowering. And body effect. Generally, body is nothing but substrate of that mass device is called body. So when the negative voltage is applied to the substrate with respect to the source, the well to source junction, the device is in the reverse bias. Means suppose if you consider NMOS device, the substrate is made up of with p-type material. So if you apply the negative voltage to the substrate p-type device, that will moving to the reverse bias junction, then it will widen the depletion region. Whenever the reverse bias is more, the depletion region width is more. So this leads to the increase in the threshold voltage. So this effect is known as body effect. Threshold voltage roll off. When the channel length is reduced, the threshold voltage of metal oxide semiconductor will be uh, decreases. So the direction of channel length is known as threshold voltage roll off. Temperature effect. As we know, for every 10 degrees rise in temperature, definitely the leakage current will be increases. So that's about temperature effect, VTH roll off, threshold voltage roll off. So the channel length is reduced whenever you are decreasing the threshold voltage. So that's about subthreshold leakage currents. Thank you.